Hello, everyone. Welcome to the last session of ATC. Today, I'm going to talk about how to provide consistency and durability guarantees when Flash is used for write-back caching. My name is Dai Qin, and this is a joint work with my supervisors, Professor Angela Demke Brown and Professor Ashvin Goel from University of Toronto. Nowadays, data centers are using centralized storage system for ease of management. For instance, hypervisor nodes in the virtualization environment store their image on a centralized SAN or NAS rather than on their local drives. We call these hypervisor nodes as storage clients. This is shown at the top of this figure. To reduce network latency and storage contention due to access from many such clients, today, many storage environments are increasingly using client-side or host-side SSD-based caching. Compared to in-memory caching, SSD provide good throughput for significantly cheaper price. Next, we show how SSD caching works. In this figure, when the client makes a block layer request, the caching layer searches the SSD cache by checking an in-memory mapping table. This mapping table maps block numbers on the primary storage to the block numbers on the SSD cache. For example, the first mapping showed the block number 100 on the storage server with the content A is actually located on block 7 on the SSD cache. On a cache hit, data is retrieved from the SSD, reducing I/O latency. Otherwise, data has to be fetched from the centralized storage. So here in this figure, I have described the read path, but what about write path? Well, we could use write-through caching where writes are sent to the storage synchronously. Write-through is reliable, but it introduces high latency for write-intensive workloads. Alternatively, with write-back caching, writes are cached on the SSD and sent to the storage asynchronously. This reduces write latency. However, client failures can cause data inconsistency and loss. So, our goal is to provide the performance benefit of write-back caching while provide the reliability of write-through. We began by examining the two types of client failures and how they can lead to data loss or inconsistency under write-back caching. The first type of client failures occurs when an SSD on the client side fails permanently, leading to the loss of all data stored on it, which we call a destructive failure. This can happen, for example, due to fire. The problem for write-back caching with this type of failure is that dirty blocks on the SSD device are lost permanently, potentially leading to storage inconsistency. The second type of failure occurs when client fails, but the SSD device is not damaged, so its data can be retrieved on recovery. We call this a recoverable failure. For example, this can be caused by a power failure on the client node. When the client recovers, dirty data is accessible on SSD, because in this case, it has not been lost. So in this figure, block 7 with content A1 is dirty. It's shown in the yellow color. The problem on recovery is that we don't know that this block 7 on the SSD needs to be flushed on block 100 on the primary storage side. Recall that this information is maintained in the in-memory mapping. So this in-memory mapping has to be made persistent. However, this converts each write into two writes to SSD, one for the data, for instance, A1, and now one for the record to the new mapping entry to A1. In this work, our goal is to provide consistency and durability for client-side write-back SSD caching, and to do so efficiently. By consistency, we mean all the data written until some point in time is available after a failure. By durability, we mean that data confirmed as written is not lost after a failure. I would like to summarize the result of this work first. We describe two caching policies. The first one achieves 20% to 70% higher IOPS compared to write-through, with the same reliability. The second one provides higher throughputs, achieving the same IOPS as writeback, but with much higher reliability. To understand how we achieve these results, we need to first examine the interface that the storage system provides to the applications. Speaking of storage interface, people usually think that storage interface consists of I/O commands for reading and writing blocks. Well, however, writes are not guaranteed to be durable because they can easily be reordered or buffered due to internal disk caches. To ensure durability, disk provided cache flush command that ensures buffered writes are actually flushed to the media. Thus, the cache flush command serves as a barrier for previous write. In practice, this cache flush command is issued by applications via fsync system call or by a file system that implements atomic operations. We also define an epoch as the duration between two barriers. Within an epoch, the flushing of blocks can be in arbitrary order for efficiency. For example, in this case, write 1 is flushed after write 2. So based on this storage interface, we propose two writeback policies: writeback flush for handling destructive failures and recoverable failures, and writeback persist for handling recoverable failures only. These policies are based on the insight that the caching system should provide exactly the same storage interface as the physical device. This provides us two benefits. First, the caching layer does not need to change the consistency and durability guarantees provided to the application. Everything just works transparently. Second, the system is efficient because it provides minimal guarantees. For instance, writes can be reordered between flush commands to reduce seeks. Now, I'm going to explain how our flush and persist policy works. The flush policy works in the same way as writeback for read and write request. For instance, all writes are cached on the SSD device and immediately acknowledged to the application, which reduces write latency compared to write through. Dirty blocks are sent to the primary storage asynchronously in the background. The key difference between writeback is that on the cache flush command, it flushes all the remaining dirty blocks from the SSD cache to the primary storage. And the mapping is marked clean after this. Note that this mapping doesn't have to be durable. Our second policy is called writeback persist policy. Again, writes are buffered on SSD device and sent to the storage asynchronously in the background. On the cache flush command, we simply persist the in-memory mapping to the SSD device atomically, rather than flush all the dirty blocks to the centralized storage. So in this case, dirty block A1 stays on the SSD after this write barrier. In this table, we compare our flush and persist policies with traditional write-through and write-back. In terms of reliability, the writeback flush policy provides the same consistency and durability guarantees as write-through on both recoverable and destructive failures. The writeback persist policy only handles recoverable failure, while traditional writeback provides no reliability at all. We also show these policies in the order of increasing performance. In terms of performance, all writeback policies have low latency for write operations compared to write-through, since they only need to write to the local SSD drive. Unlike write-through, the flush policy have high latency for cache flush operation because all dirty cached block must be committed to the centralized storage before the operation can be acknowledged to the applications. The persist policy have low latency on cache flush command because only the mapping has to be persist to the local SSD device. Finally, writeback does nothing on the cache flush command, and this is why it doesn't provide any reliability. In our design, we use a copy on write B tree to implement the mapping table so that it can be persisted to the SSD device atomically. This ensures that the mapping is consistent with the cached data. Our implementation persists only the changes to this table, and these changes are written out sequentially to the local SSD device. Together, this makes persisting the mapping table an efficient operation. Recall that we flushed 30 blocks to the SSD device asynchronously. We have implemented 2 flushing optimizations based on reordering writes within epochs. This reordering is allowed by the storage interface. First, ascending order flushing. Flush blocks in the order of primary storage block numbers to reduce disk seeks on the primary storage. Second, epoch-based flushing allows flushing blocks from a previous epoch concurrently with the writes to the current epoch. Our paper described these and other optimizations in details. For our evaluation, we use a client and iSCSI storage server. The server uses a software RAID 6 with 13 standard 7.2K RPM Hitachi drives. The server and clients are connected using a 1 gigabit Ethernet. The client is a 16-core machine with an Intel SATA SSD attached to it. We limit the client's physical memory to 2 gigabytes and use only 8 gigabytes of SSD for caching. This is to emulate a typical mid-end storage configuration in the production environment. We use 3 types of workloads in our evaluation. The web server workload is read-intensive. We use 2 configurations, a small and a large one. The small configuration is 4 gigabytes. Recall that the size of the SSD cache is 8 gigabytes, so the small configuration fits entirely into the SSD cache. The large one is 14 gigabytes, so the large one does not fit in. The MS-NFS workload is a write-intensive workload. Again, we use a small and a large configuration. The small configuration have 87% of the requests are write requests, while the large one contains 57% of the requests are write requests. The third type of workload is varmail. Varmail is a sync-heavy workload that issue a small number of random reads and writes between each syncs. We run these workloads for 20 minutes, allowing the first 10 minutes for the cache to warm up, and then measure the IOPS for the next 10 minutes of the experiment. This graph compares the performance of our caching policies. We show the performance in IOPS on the y-axis. For no caching, write through our writeback flush, writeback persist, and the writeback policies in the order of increasing performance. On the 2 left plots, we show the read-intensive web server workloads. These plots show that all caching policies have similar performance, which is for read-intensive workload, which is expected because this workload actually a very small amount of writes. For write-intensive MS-NFS workload, our writeback flush policy reduces write latencies and thus providing much better performance compared to write through, while providing the same reliability. Our persist policy performs comparably to traditional writeback because persisting the mapping is an efficient operation and there are few syncs in these workloads. Notice that the persist policy provides much stronger reliability guarantees than writeback. For sync-intensive varmail workload, writeback flush performs no better than write through because there are very few writes operation between syncs and it syncs frequently. The persist policy performs significantly better because dirty data can be cached on the SSD across syncs, and the mapping can be persisted efficiently. In conclusion, we have designed and implemented a client-side SSD caching system that uses Rightback Caching for performance, while providing the same consistency and durability guarantees as underlying storage. We do so by leveraging the write barriers issued by the applications. We designed 2 policies, The writeback flush policies provides the same reliability as write-through with much better performance. And the writeback persist policy provides consistency and durability on recoverable failure with the performance comparable to traditional writeback. Thanks, now take questions.
I'll start with a question. This work is clearly motivated, and in fact, it's so clearly motivated that I really wonder why writeback caching hasn't been used as even a common practice. Is there any insight in terms of like what was the challenge or what was the caveat that I haven't realized in terms of using the writeback cache and why it hasn't been a common practice in data center storage?
I guess so just to clarify, the question is the real challenge why industry does not deploy writeback caching. I guess the big concern is the client crash or like VM migrations. In these cases, you need data not only to be consistent but highly available. So in this case, where you have a client-side cache and you migrate from one node to another, the cache also needs to be migrated. Well, in our case, we have also examples for this type of failure thing that the client, as well as with the SSD, failed. You cannot get the data back on the SSD. And now you only have the primary storage. So it's more of a data availability and integrity issue.
So, Howie Huang from George Washington University.
Excuse me, I can't hear you clearly.
Howie Huang from George Washington University. So my question is, what if you have multiple concurrent running applications that do you have to worry about that the other clients may not see the data in enough time? Do you have to worry about application level semantics in some cases? So
just to clarify the question, are you saying that multiple storage client can share part of the data?
Right.
So we in our setup, this is not allowed. We're not taking that into consideration. This is like data center well-partitioned storage. So before you even have the cache, the storage on your centralized storage is well-partitioned already. There's no sharing in between.
Okay.
Thanks.